Hello everyone, here's the project presentation of EE538. Our team members are Chanjuan and Shaoen. In step 1, we need to realize the function of autocomplete the location name, and when the user inputs the partial name of the location, our system will return a list of possible locations name. First, we traverse all nodes on the map. If the beginning part of a location's name is equal to the input, we will add to the location name to our output vectors, as it's shown in the results. And the total time complexity of this algorithm is all of n. In the second step, we need to find the coordinates of a name in the map. So we can see that we use the getID function, which has all of n complexity, and use the getLat and getLong. They both have the time complexity of all of 1. As a result, the total time complexity of this function is all of n. And we can see from the running results, if we input the location is roughs, we can get its longitude and latitude. In step 3, we need to calculate the shortest path between two places. The first algorithm is Dijkstra. We choose to use a priority queue to create a min heap. In this way, it's easy for us to find the unvisited node with the shortest distance. The time complexity here is all of E plus V log V. Here, E is the number of edges in the graph, and V is the number of vertices in the graph. The second algorithm is Bellman-Ford. We create a neighbor map storing the node that needed to be visited and its neighbors. Here, we will erase a node after visiting it to avoid visiting the node again. This step can decrease the runtime significantly, and the time complexity here is all of E times V. We can see from the runtime comparison that the runtime of Dijkstra is much less than Bellman-Ford. Step 4, Traveling Trojan. In this function, we use two methods to realize it. The first one is backtracking algorithm. So we can see from the runtime comparison that when the number of places is 10, the runtime boosts a lot compared to when the number of places is 5. And this animation shows the process that we find the shortest path to traverse all nodes in the input location IDs. And the time complexity here is all of n factorial, since we need to calculate the distance of all the past permutations. The second method is to use the two-opt algorithm. We can see from the runtime result that when the number of places is 10, the runtime is only 10 times to the number of places when that's 5. And here we can see that the total time complexity is all of n cubed. And in this 2 for loop, the time complexity is all of n squared. And in the while loop, the time complexity is all of n. Thus, the total complexity is all of n cubed. And this graph shows the process that we find the shortest path to traverse all the nodes. And we can see from the table that if the number of places is less than 4, the runtime of backtracking is less than the two-opt algorithm. However, as the number of places increasing, the runtime of two-opt will be much less than the time of backtracking. Step 5, cycle detection. We traverse all nodes within the subgraph and run a DFS function to check if there's a cycle. Within the DFS process, if we meet a neighbor is in the square and is visited and it's not the parent node, then cycle exists. The total time complexity here is all of V plus E. And here the result shows that we detect a cycle. Step 6, topological sort. We can get the topological order after inputting dependencies vector and the vector of nodes. And the result shows the topological sorts results of our input. So the total time complexity here is all of v plus e, since we need to traverse all the nodes in the given dependency vectors. Step 7. Find k closest points. As we can see in the result, we can get the 5 closest points of graphs. Here we construct a class called point, which includes the name of the places and the corresponding distance to the input string name. And we use a maximum heap to keep the order of points. If the size of maximum heap is bigger than k, we pop the top of the heap. While the maximum heap is not empty, we get the top element of it and add it to the front of the result vector. The total time complexity here is all of n times log k. This is all the content of our presentation. Thank you for your listening.